Okay, so I think we'll make a start now. So for the first of our invited speakers for this section, we have Professor Colin Torney from the University of Glasgow, who's going to talk to us a little bit today about machine learning for animal populations. So over to Colin, thank you.
Hey, thanks very much. So thanks to the organizers for the invitation, and thanks for coming. So today I'm going to talk about two projects. So two projects largely relating to wildebeest. So most of my work is on wildebeest population dynamics and migration. But I'm in the maths and stats department, so a lot of what I do is quite generic. It's sort of methods development and thinking about these problems more broadly. So I'm going to talk about two separate projects. One is more classical machine learning, and the second one is more the interface between statistics and machine learning, where we're using statistical models but borrowing techniques from machine learning to fit these models. So the first project is about activity classification. And as I mentioned, I mainly work on wildebeest migration. And for those of you who don't know, the wildebeest migration, or the largest population of wildebeest in the world, live in the Serengeti National Park, which is shown here in the center. It's a very famous national park in Tanzania. I'm sure you've all seen the nature documentaries. These are the animals that often get eaten by the crocodiles or the lions. So this is in East Africa. So Tanzania here. This is the Kenyan border. Rwanda, Burundi. This is just to localize you on the map. And within the Serengeti National Park, there's a few organizations that work there and protect the park and monitor the ecosystem. And we work very closely with Tanzania National Parks, or TNAPA, and Frankfurt Zoological Society. And over the last few years, what they've been doing is introducing an array of gateways that they're using to collect data about the park and monitor what's going on in real time. So the red dots are the locations of these gateways. And they're distributed throughout the park. They primarily have a focus on monitoring the rhino population. So they tend to be clustered around areas where where the rhinos tend to be, because these are the most under threat and valuable species in the ecosystem. And they also use them to monitor rangers. So the vehicles that they use to monitor the park have transmitters within the vehicle, so they can get a real-time view of where the animals are, where the rangers are. So if they detect a threat, they can mobilize and move nearby rangers to the location where they think they need to be. So this is just an image from the monitoring station. So this is where they're taking the data from these gateways and monitoring what's going on. So that's a very nice system. A lot of infrastructure is already there and in place, and we want to take advantage of this infrastructure and try to leverage this infrastructure for the ecological monitoring we're doing on the wildebeest. And we do that using GPS collars. So we put collars on wildebeest, and that tells us where they go and how they're moving through the national park. So previous generations of these collars use satellite communication, and they're quite expensive. They're quite they go through a lot of battery, and they last about 2 years. So we were trying to make use of this new gateway array and develop a collar that was cheaper, that was allow us to deploy more collars and would last longer. And we were also keen for these collars to be able to tell us not just where the animal was, but also how it was behaving. So it's not just location, but it's also behavior data. We tried working with companies that developed these collars for a number of months, but we couldn't quite get a product that matched our requirements. So in the end, we ended up designing a custom collar. And the first iteration of this collar is shown here, and we're using components, off-the-shelf components that you can buy and program to run these tasks. So we have a radio. This is a microprocessor unit from Arduino. It has a little radio communication that we can transmit the data. It has a GPS here, and it has an accelerometer there, or an inertial measurement unit. And then we 3D print the case, and then we can make it watertight, and it's something that we can put onto the wildebeest. So if we want to collect data along with behavior, we want to collect behavior data along with location, then we really need to be able to process the behaviors on the device, because the accelerometers give us a lot of data. It's very high frequency data, but we can't transmit that amount of data over the network. So we need to be able to process data on the device, and for this we use this tiny ML library called Eloquent ML. And if you're familiar with TensorFlow, which is very similar to PyTorch, if you're not familiar with TensorFlow, it's just a way to build neural networks. And this version of it is this really condensed version that allows you to make these models very small and put them on these tiny microprocessors. And this is the architecture we ended up using. So one thing to notice about this neural network is that it's very small. So if you're used to looking at these types of networks for image data, typically you see tens of convolutional layers going through here. Because we're so constrained by the memory capacity of the devices, we only have 3 convolutional layers, and that just processes our inputs, which is the raw accelerometer data, and it comes up with a prediction, which is the last layer. It gives us these 4 classes, which is a probability of each behavior. So much smaller than the standard neural networks you will have seen. So we need training data. We could get training data from the Serengeti. The problem there is that once you deploy these collars, wildebeest are very unhappy about the collaring process. They tend to, afterwards, they tend to just disappear very quickly. In these large herds, they're very hard to track, they're very hard to relocate. So instead of going directly to the Serengeti to collect training data, we went to a smaller population, captive population or semi-captive population, which is located in this golf and wildlife estate, which is close to the national park. It's about a 2-hour drive from the national park. And this resort is a very fancy, very expensive golf resort. And they also have a sort of a wildlife park adjacent to the resort. And that's where they have this population of wildebeest and eland and other species. So we went there in, I think, late 2022 to tag these wildebeest. And one thing to note is that the huge difference between this is from their website, so this is sort of an advertising picture, but it does look like this. The golf course is immaculate, and then the wildlife park, not so much. So the wildebeest were really struggling. There was a lot of drought that year, and there had been for the previous 2 years. So there was a lot of quite unhealthy wildebeest. But we collared them, and because they were in this semi-captive arena, we could go and monitor them each day. Once we put the collars on, we could go and watch them and record what they were doing. So this is the wildebeest. We put out 6 collars, and this is one of the collars out. And you can see it has the color coding, so we know which collar is associated with which wildebeest, and we can tell when we're collecting the data, we've got the right, we're watching the right wildebeest that we're collecting data from. So we spent about 2 weeks on this golf resort, just following wildebeest around all day, every day. We used a slightly different version of the collar because we were very close, so we used a Wi-Fi connection, and that allowed us to connect to the collar, and the collar would transmit the raw accelerometer data. So it's like 5 Hertz data, these 5 axes of acceleration and orientation of the collar. And then as we were doing that, we recorded the wildebeest with the video camera, and we also followed them around. We had a secondary device where we would monitor, we could log the behavior. And we were looking at 4 different behaviors. There's walking, grazing, lying down, and just standing. So as the wildebeest transitioned from one behavior to the other, we just pushed the button on the logger, and that would record what the wildebeest was doing. And then we had the live stream of data. And then we used the video recorder just to fine-tune those labels so we could extract exactly when the transitions were occurring. So once we had the training data, we could train our model. What I'm showing you here is the confusion matrix for the validation data. And what we were quite happy with this. I mean, I should say this is quite an easy classification task. It's not a difficult task. If you look at the raw data, we have head pitch, we have acceleration, and sort of the up-down direction and the left-right direction. You can look at the data and see when it's moving, when the head's down. So it's So the algorithm, we were fairly confident when we looked at the data that it should be able to classify quite accurately. So when it's grazing, the head is down. We can see that very clearly in the orientation of the tag. When it's walking, obviously you see the movement. Standing and lying was something that we weren't expecting it to be too accurate with, but it turned out to be reasonable. And the difference between standing and lying is that when the wildebeest are lying down, the head tends to be tilting up, and when they're standing, it tends to be sort of tilted down, and you can detect that. The one concern with that is that the wildebeest in the captive arena don't have any natural predators. In the Serengeti, they do. When they're vigilant, the head tends to be up. So we think there could be some effect that when we try and generalize to natural populations, we're going to miss out on that vigilant behavior and interpret that as lying, when in fact it's just standing and being vigilant. I think most of the confusion between classes like standing and walking is because the wildebeest is constantly transitioning between these behaviors, and we look at 10-second bursts of data and classify those. And what we see is that when they're walking, they tend to walk, stand, walk, stand. So within 10 seconds, you get this mixed sort of same behavior within an entry in the training data, which we label with the majority. So if it spends most of the time walking, we call the whole thing walking. I think that's what a lot of the confusion was about. So once we had the algorithm trained, we then deployed these collars. So this is a pilot study. So we did 8 collars April 2023, and the aim is to scale this up over the next 2 years to be 100 collars out. And these collars are collecting data on behavior and location. They're solar powered, so in principle they could run forever, and they transmit to the LoRa gateway, and they record a GPS location every hour, and then we get 30 minutes of behavior per hour, and then it rests. The collar just goes to a dormant state for 30 minutes, and that's just because that's what we thought would be enough processing to give us information about the animals, but at the same time not run down the battery and just allow us to run indefinitely. So each 10 seconds we classify as one of 4 behaviors, which we encode as 2 binary digits, and then we had to really compress this down, get it as small as possible, so we can get 30 minutes of data down to 45 bytes. And this is important because of the nature of the LoRa network. So this is not like a mobile phone network. Data is very constrained. You can send data a long way, but you can't send very much. So we just came under this 51 byte packet size limit, which meant we could use the longest range communication possible and not have to break our packets up into individual components. And the challenge here is that a lot of these, when you're transmitting the data, a lot of it isn't received. So you're transmitting over 50 to 100 kilometers. Sometimes it gets through, sometimes it doesn't. So you just keep sending it until you get the acknowledgement. So this is April 23 when we deployed the collars. As you see, it's much greener than the captive arena or the golf course where we got the training data. And in general, the wildebeest were just much healthier, much happier, which is kind of reverse to what we originally expected, that we thought that the Serengeti wildebeest would be hungry and a bit miserable, and the captive animals would be happy and healthy, but it was completely the opposite. And yeah, so this is the collar with the solar panel on top, and yeah. So we ran we put these out last year, and then we just monitored the data. As I say, we did try and follow the animals so we could validate the classifications on the Serengeti wildebeest. It was just impossible to follow them. Within 5-10 minutes, they were just lost in the herds, and we couldn't relocate them. So we had to try and come up with ways that we could see if our sanity check our results and make sure that what we were getting from the collars was actually reasonable. So the first thing we looked at was how far they travel, how far the GPS is telling us they move, and how much time they spend walking according to the accelerometer. So if you see them moving a long distance, but the accelerometer tells you they're lying the whole time, then that's going to be a problem. That's something we could think, well, okay, well, maybe we're not classifying correctly. So we do only classify for 30 minutes. So it could be that they lie for 30 minutes and they walk really fast the other 30 minutes. But what we see is that there is linear relationship between the proportion of time they spend walking and how much distance they cover, which is what we would expect. And that's just a kind of fundamental sanity check that we performed. We also looked at the GPS locations, and we saw reasonable, everything seems to be working fine. We're at much higher resolution than the previous collars, which would only give us 1 or 2 fixes per day. Now we get hourly fixes, so we can really see these fine scale movement decisions. And then we looked at the patterns of activity throughout the course of the day. So what we're looking at here is the probability that a wildebeest will be adopting one of these behaviors at any point during the day. We fit this with a Gaussian process regression model, and it allows us to quantify uncertainty. The shaded regions are the typical sort of twilight, or sorry, dawn and twilight time. So this shows you when it's daylight and when it's night. And we got results which were very pleasing to us because they validate what we would hope for. This is how the behavior that we observe in the field. So at first light, there's a lot of grazing. They tend to settle down when it gets hot in the middle of the day, and then in the evening they're active again and grazing again. So we see, there's quite a lot of uncertainty, but without the uncertainty, this is what we would predict before we deploy the collars. This is the type of pattern we would expect to see. So lying down at night, more active during the day. They do follow these quite clear daily cycles, and we were able to detect those, which was good. So that was the upside. Downside was that we really didn't see a lot of robustness in these collars. So this table is something I downloaded from the LoRa system. It was actually last year, but there hasn't been much update since then. This tells you the last time the collar was heard from. So we deploy these collars. We've got no way to track them down. We don't know why they fail, but we just hear from them now and again when they're in range of the gateways. And what we saw is that there's a few collars that we deployed in April, and we just heard from them at the end of April, these two, and we didn't hear from them again. And then as the year progressed and more of these collars, we just stopped hearing from them. And we don't know if they're just out of range. I mean, at this point, they're probably not coming back. But it gave us the data. It kind of was enough to tell us this system could work, but it wasn't robust enough for us to be confident we can go out and deploy the next 100 collars if they're only going to last 6 months or less in some cases. So what we're working on now is refining our design and going back to the actual design of the circuitry and seeing, can we make this a bit more solid, a bit more robust. One issue we think might be a problem was the type of battery we're using, so we're replacing that using a more expensive, hopefully more reliable battery, and then redesigning. So instead of using these commercial components, we're putting the GPS and the radio directly on the PCB, and we're actually working with a company in Glasgow, European Circuits, who are this amazing company that are just very, very helpful, very friendly, and they've been manufacturing these for us, and they're very patient in all our design questions and all our messing them about. So that's the end of the first part of the talk. And now I just want to talk about a slightly different aspect of my research, which is more on the sort of statistical inference side. So the first project is really a standard machine learning approach, classification challenge. And really the challenge there is just in the implementation. There's nothing new in the methodology. It's just about actually implementing in these real systems. And now I want to talk a bit more about how we use the data we get and how we make inferences at the population level. So the wildebeest within the national park, they're constantly making decisions about where to move. There's a lot of threats in their environment, and these are both sort of man-made. So we're seeing a lot more tourist lodges. We're not seeing more roads, we're seeing more traffic on the roads. So there's a lot of commercial traffic going through, a lot more tourism, especially since COVID, it seems to pick up. And there's a real investment a real focus in Tanzania on building tourism as the key driver of their economy. And they have quite ambitious targets to get to certain numbers of tourists per year. And pretty much all tourists that go to Tanzania at some point go to the Serengeti. So increases in tourism in the country means increases in the national park. And there's also these natural threats. So these kind of copies like this is where you can expect to find predators. They also have to undertake these river crossings. So all these elements of their environment are affecting how wildebeest move. And the collars give us a way to infer how they respond to these environmental threats, but they don't tell us how the population of wildebeest as a whole is distributed. And the population level is what we really care about. We don't really care too much about an individual wildebeest and where it moves or how it behaves, but on the population level, we want to know if we put a hotel in a certain location, what kind of impact is that going to have on the distribution of wildebeest and how well they can survive. So this figure is from a paper a few years ago where we took this very crude approach and looked at the distribution of wildebeest over time. So this is on 55 wildebeest over the course of 10 years. And we just looked at where they were on average, what's the probability of finding a wildebeest in a certain location of the national park. So that's a very crude estimate. But what we'd like to do is understand how they respond to threats and then use that information to try and build a picture of this distribution. So from the fine scale movement decisions, what will that naturally lead to at the population level in terms of the spatial distribution? So fortunately for us, there was this very nice paper a few years ago by Theo Michelot, Paul Blackwell, and Jason Mathiopoulos. And Jason, some of you may know, he's actually a professor in Glasgow. And they came up with this approach that does exactly this. So it's a mathematical method or a modeling framework that allows you to link fine scale movement decisions and use these fine scale movement decisions to come up with a long-term prediction of space use. So this equation here is the utilization distribution. So this is telling you the probability of finding an animal at a particular location given the covariates. So these are the environmental conditions at that location. And these could be sort of grass vegetation or greenness. It could also be distance to the nearest hotel or distance to the nearest road. And the novelty of what they did in this paper was to come up with a movement model that naturally gives rise to this distribution. And the trick that they employed was this two-stage movement process where you imagine the animal takes a random step at first. So it goes from, we get this right, from ZT, it can pick at random and it chooses the step C, and then when it's at C, it chooses based on the environment. And because of this sort of artificial process of movement, it's reversible, and they were able to show that you can interpret this as a MCMC sampler, a Gibbs sampler, if people are familiar with that. So it's like the animal is performing a Markov chain Monte Carlo sample, and because of that, the long-term utilization distribution there's a correspondence between the long-term utilization distribution and the properties of these fine scale decisions. So that was something we were very interested in. The one question we had about that was, okay, so this gives us a likelihood of a step. And so you can calculate the likelihood of all your steps, all the movements the animal made, and you can make maximum likelihood estimates of your movement parameters and your responses to the covariates, but it doesn't tell you anything about the uncertainty. So we're really interested in not just about, not just predicting how wildebeest will respond to a road, but quantifying the uncertainty in that. Because some of these features are very rare, some are very common. What I'm showing you here is an example movement data set. This isn't wildebeest, this is from another paper, but it just shows you these different environmental fields, and hopefully you can see the trajectory. It's the same trajectory in all four. So this is the trajectory of a GPS collared animal. So we have population density, human population density, elevation, and then we have these categorical variables for grass. So is the landscape classed as grass and a wet area, or is it a forest? And what you can see here is there's very little grass available to this animal. So when you're trying to make, if you're trying to make an inference about whether it's avoiding or attracted to grass, if you neglect uncertainty, then you're neglecting the fact that there's very little data that you're making these assumptions on. So we wanted to try and take this method one step forward and quantify the uncertainty in these predictions or on these parameter values. So to do that, we use variational inference. And in this approach, so it's an approximate Bayesian inference. So we have our posterior distribution, and if you're familiar with Bayesian statistics, you'll be familiar with the posterior distribution. We don't know the posterior, and the standard approach would be to sample from it using MCMC, but that's quite slow. So instead, we use variational inference, where we introduce an approximation to that distribution, which we call Q. So, for example, we might say, I don't know what my posterior is. I'm going to assume it's a multivariate normal distribution, and then I'm just going to try and choose the values of that multivariate normal, the mean and the covariance matrix, to match as closely as possible. And closely as possible in the context of variational inference means you minimize this KL divergence term. And then the trick of it is, because you don't actually know this posterior, you can't minimize that directly, the distance directly, but you can manipulate this, and you can find out that you can rearrange so it doesn't actually depend on this posterior, and you can find out it's this. If you maximize this term, then it's equivalent to minimizing this term. And you can see that this is roughly equivalent to fitting the data term, so matching the data as closely as possible, and this regularization term, which sticks you to your prior distribution. So those two terms balance out and allow you to fit a model that matches the data but doesn't go too far. I just thought I'd show some code, just because if people are used to sort of machine learning and using sort of training deep learning algorithms, if you would formulate, if you go from sampling to optimization, the nice part of it is that there's all these techniques in deep learning and all this code and libraries developed for training neural networks that we can just borrow. So we use TensorFlow a lot. So we're using the Keras library. So we subclass of Keras model, and this is now a movement model. But we can just use everything else beyond that. We can just use standard operations, so TensorFlow data sets. We can use the Keras optimizers. So we use just plain gradient descent, but we could use Adam or any other ones that are coded in. And there's also this nice convergence diagnostics or early stopping criteria, which just make things a lot easier. You don't have to rewrite all this code. So going back to our earlier example, so we run it on this model, on the test case, and then we get predictions of parameter values and uncertainty quantification. So what we see is that we have high uncertainty. So if you look at the graphs, okay, so it does seem to avoid graphs, which is what we would say if you look at the map, but there's really high uncertainty in that estimate. So there's not much we can say there. And things like human density, so that's this one. We really can't say anything about the response to population density. It's, if we look at the maps, there really isn't any human population there. So anything we say is just guesswork, and we can see that we get that in the posterior distribution. So just very quickly, how we're applying this to the Serengeti. So the first thing we're looking at is buildings. So there's a lot of new construction going on in the national park. There's a very nice data set called Open Buildings, which was created by Google. And this uses object detection and satellite images to find the location of all buildings across the globe. And so we looked at this in the context of the Serengeti, and we see, so you can just see the construction. So the black dots are the locations of buildings, and you can just see them sort of right up the edge of the national park. They're really just, wedging all these animals in, but also a lot of construction going on within the park itself. So we fit our model to that, and then we don't have sort of a building at every location, but we can think about the distance to buildings and how animals respond to the distance to these to locations, and whether, given the choice between a location close to a building or far away from a building, they're going to go far away from the building. And so we see this really strong negative effect of buildings, that they're selecting areas where buildings just aren't present. And this is the utilization distribution you would get if you just assumed wildebeest were following these buildings. So that neglects the migration pattern, but if we just look at buildings, this is the utilization distribution throughout the national park we would expect. Okay, so I think I'm a little bit over time, but just to acknowledge the collaborators. So Cyrus Caprelli is a PhD student who worked on the first project. Majaliwa, Cyrus is an ex-PhD student who graduated last year. Majaliwa is a current PhD student, and he worked on the second project and the funders there. Thank you.
Great, thank you for the talk. So over to questions. I see a couple of hands, I think.
In the results for your movement classification, there was a bump in the early hours of the day for both standing and lying. Is that a hangover from the uncertainty in being able to classify between those two?
So standing here, lying here. You mean this overnight?
Yeah.
Yeah, it's hard to say. I mean, I think they do. It's not like all night they lie down. So there is a lot of time they just be standing at night. And right now we just don't know how much. You know, we have the confusion matrix. We can understand how they behave on the training data or that system, but we really don't know how they behave in the Serengeti. So I'd say it's possible that this is just, you know, these periods of standing. Well, I mean, I think what we'd be saying is these lying behaviors we're predicting may well be standing and being vigilant, and that's possible. But at the same time, they do tend to rest at night, so they would be lying down. So yeah, we can't really tell which, you know, whether it's misclassification or how they actually behave. We are trying to get data on the Serengeti wildebeest right now. So we've had a postdoc follow them around and try and film them, but we don't have the data yet.
Okay, maybe one more question, I think.
Cheers. Thank you for the talk. I've just got a question about, you know, how you mentioned that a lot of most of the collars would sort of just disappear from the radar.
Mm-hmm.
And obviously, I'm guessing you can't really track them down now that they've disappeared. I mean, obviously, they're still there somewhere, but you just don't know where they are. In terms of the effects of that on, obviously, you've now just got collars just on wildebeest, and maybe if the wildebeest gets eaten by a lion, the collar just either the lion eats it or it just sort of goes onto the ground and it's kind of littering, I guess, technically.
Yeah.
Do you know if there's any ways, maybe for future work, how that could be mitigated? So if you do lose contact with your collar, like it's probably quite a hard problem to solve, but have you given any thought to that?
Yeah, no, it's something we think about a lot. So the other collars we have, you know, they have a VHF signal on them, and they also have a mortality signal. So when they detect mortality, they will signal, and then someone can go and find them based on the nearest location and the VHF beacon. So if you get within a few kilometers of the collar, you can use the VHF beacon to find the collar. So we are going to put VHF beacons on the next batch. The challenge is you have to be within range first, so you have to get to the rough location. And how we're going to do that is by increasing the coverage of the network. So the main work that's going to go on next year is improving the robustness of the collars and also increasing the network coverage. So what we're going to do is have a parallel network, so split off from the vehicle tracking network, because there's a lot of traffic on that, sort of radio traffic, not vehicle traffic, but that kind of blocks up the network. And we're going to have a designated wildlife network with more coverage. So if it's in range, we're okay. You know, we know where it last was, and then we can go and find it. So hopefully that's going to avoid that problem. But I mean, yeah, it's scientifically it's a problem because we don't know why it fails. But also, you know, there's also these collars just dotted around. Yeah, so we would like to get them back and yeah, dispose of them. Probably lions don't eat them. They do chew on them, but we do. So you will find a kind of a wildebeest skeleton with a collar. That's all that's left at the end of it. But yeah.
Thank you.
Okay, so I think just in the interest of time, we'll leave it there. But again, if you have more questions afterwards, feel free to speak to Professor Torney. And let's thank him once again while we set up for the next speaker. Thank you.